In this year, that is 2020, or rather for this year, 2021-2022, haloalkanes and haloarenes is appearing in term 1, and it, along with alcohols, phenols, and ethers, as well as biomolecules, carries 10 marks, if I am not wrong. I'll just confirm that. 15 marks, right? So this is the basic syllabus included, so you have to learn basically everything in the chapter. And I believe the last topic of the chapter, that is poly halo compounds, are the only ones which have been exempted for this year. So let's begin. So in the chapter Haloalkanes and Haloarenes, we are learning about carbon compounds that consist of the functional group, and in the functional group is a halogen atom. So halogen compounds are classified in three main ways. First is based on the number of halogen atoms. So monohalogen atoms will have only one, di will have two, and tri will have three. So this is the first type of classification. The second one is compounds that contain an sp3CX bond. So in case of an sp3CX, we have it classified as an alkyl halide, an allylic halide, and a benzylic halide. Let me just zoom in a little. So an alkyl halide has the general formula CnH2n plus 1x. So here, the alkyl halide is further classified as primary, secondary, and tertiary based on the carbon atom the halogen atom is bound to. So here, in case of primary, this carbon is only bound to another alkyl group. Secondary, it has two, and tertiary, it has three alkyl groups. So remember this classification because it's very important, or rather, remember these structures because they're very important when we study about the structure, the chemical reactivity. Next is allylic halides. So allylic halides, if you see over here, you have a double bond, right? And this carbon atom has a single bond with the double bonded carbon atom. So this is an allylic halide. Similarly, over here also, you have this carbon atom having a double bond, but this carbon atom is bound to a double bond containing carbon atom, and that is why it is called an allylic carbon. Next is benzylic halides. So benzylic halides, as the name suggests, you have a benzene ring and you have another carbon atom which is attached to the benzene ring, to which the halogen atom is attached to. So it can be, so here in this case, if you see, you have a carbon over here, the R1 and R2 can either be methyl and a hydrogen, and if it is a methyl and a hydrogen, it is a secondary carbonate, secondary halide, whereas if these are both alkyl groups, then becomes a tertiary halide. Next, based on compounds. So compounds can also be classified based on the fact that they have an sp2CX bond, which means this carbon atom already has a double bond. So we have two main classifications. You have vinylic and arylic. Vinylic is when it is bound to the carbon atom, which is sp2 hybridized. So over here, as you can see, this carbon atom is sp2 hybridized, and it is also bound to a halogen. Whereas in case of aryl halides, you have the carbon atom, it's a benzene ring, that's why the name aryl. So you have the halogen atom bound to the benzene ring. So it's an sp2 hybridized carbon atom of the aromatic ring. I'd rather say aromatic ring because any aromatic ring is considered, okay? With that, we're done with the classification of halogen compounds. We're talking it based on the number of halogen atoms, compounds containing sp3CX and compounds containing sp2CX. Number is further classified as mono, di, and tri. Compounds containing sp3 are further classified as alkyl halides, allylic, and benzylic halides. Alkyl halides are classified further based on the number of carbon atoms the carbon attached to the halogen atom is attached to. So you have primary, secondary, and tertiary. And in case of compounds containing sp2CX bond, are further classified as vinylic and arylic. With vinylic, you have the halogen atom attached to the sp2 hybridized carbon atom. And in case of arylic, the halogen atom is bound to an sp2 hybridized carbon of the aromatic ring. With that, we're done with the classification of alkyl, or rather haloalkanes and haloarenes. Let's look at the nomenclature of haloalkanes and haloarenes. So first of all, you have the common name. The common name is basically the alkyl group followed by the name of the halide. So the common name for this is propyl bromide. This is This is again going to be isopropyl bromide. This is going to be isobutyl chloride. So it's just the alkyl group followed by the name of the halide. In case of the IUPAC name, it is not going to come up as a suffix, but halogens are going to be written as prefixes. So here, this compound is 1, 2, 3. 3 carbon atoms, so it's a propane, obviously. And the bromine is attached to the first carbon atom. So it's a 1 bromopropane. This is 2 chloropropane. This is 1 chloro, 2 methyl propane. So the thing you need to remember for halogens is that the name, the halogen, the name of the halogen atom is written as a prefix and not a suffix. Next is the monohalogen derivative. For monohalogen derivatives of benzene, the common as well as the IUPAC names are going to be the same. So for example, here you have bromobenzene. Bromobenzene is a monosubstituted derivative of benzene. So in case of bromobenzene, it's going to be the same in both the common name as well as the IUPAC name. Secondly, here you have two substituents. It's at 1 and the 3rd position. So 1, 3 is going to be meta. So 1, 2 is ortho, 1, 3 is meta, and 1, 4 is para. So when we're talking common names, you can write meta M, but if you're talking IUPAC name, you'll be writing 1, 3. And in case of tri-substituted, you have sim tribromobenzene, and the respective positions are denoted by the IUPAC name. Now, when we have a haloalkane over here, and this is basically, you have chlorine, right? So 1, 2, 3, and you have 2 methyl groups at the second carbon atom. So based on the alphabetical order, chloro gets first. So 1 chloro, 2, 2 dimethyl propane. This is again 2 bromo propane. Now when we have an alkyl, a haloalkane with 2 halogen atoms, it can either be an alkylidene or an alkylene. So geminal dihalides have both the halogen atoms attached to the same carbon. So this is a geminal dihalide, whereas a vicinal dihalide would have the halogen atoms attached to 2 different carbon atoms, or basically they are present in the carbon atoms which are adjacent to each other, beside each other. So that's vicinal. Geminal is both of them being attached to the same carbon atom. So ethylidene dichloride, ethylene dichloride. Whereas in case of IUPAC, it's pretty straightforward. So you have 1, 1 dichloroethane and 1, 2 dichloroethane. Here in this table, you have some common as well as IUPAC names of these structures. So do go through it. The basic rules of the IUPAC nomenclatures does get followed here as well. So if you have finding this difficult, I suggest you just brush up that and then you can come to this. Now, our halogen atoms are on the right side before the noble gases in our periodic table, which means their electronegativity is going to be extremely high. So halogen atoms are more electronegative than the carbon atom. And because of this electronegativity, what happens is the bond which is formed between the carbon and the halogen atom, the electrons of this bond is pulled more by the halogen than the carbon. And this gives rise to a partial positive charge on the carbon and a partial negative charge on the halogen. And one more thing, as we go down the group, the size of the halogen atom increases. So the bond length will vary with respect to the size of the halogen atom as well. So bond length of CF is less because of fluorine being very small compared to Ci, where iodine is very big compared to fluorine. So that's about CEX bond. So the nature of the, oh, sorry, this is supposed to be not oxygen, it's halogen. But yeah, so the nature of the carbon halogen bond is polarized, and this is because of the presence of an electronegative or highly electronegative halogen atom compared to that of our carbon atom. Preparation of haloalkanes. Now, preparation, it's always better, as I told in mentioned in one of my previous videos, for understanding and learning reactions, I suggest you write all the reactions under that particular subheading on the top. And then when you look at this, you should be able to recollect the types of reactions that are taking place. So first, let's start with the preparation of haloalkanes. So from alcohols, you have a bunch of reactions there, right? So what I did here is split it and I put it under each basically gave it a separate subheading, so it's easier for you to understand and remember it. So first of all, alcohol's reactivity is going to be tertiary is more reactive than secondary, which is more reactive than primary. Now in alcohols, the hydroxyl group is going to get replaced by the halogen atom. So we're just replacing the OH with an Cl in this case. So this reaction can be done in three ways. We can use concentrated halogen acids, or we can use phosphorus halides, or we can use thionyl chloride. Now, out of these three methods, thionyl chloride is preferred. The reason being the SO2 which is formed and the HCl which is formed, they're byproducts. Usually when you have a chemical reaction, which is quite difficult for us to separate the products from the byproducts. And we have various methods of preparation, which you probably would have learned from grade 11. So to avoid all of that, here in this case, you have sulfur dioxide and hydrogen chloride leaving as gases. And because they leave as gases, they make it very easy for the separation of the alkyl halide. Next, you have reaction with HCl. Remember, concentrated halogen acid. So what happens is you have ROH. It is reacting with HCl in the presence of zinc chloride as a catalyst. And this leads to the formation of the alkyl halide and water. Now, in case of primary and secondary alcohols, we require the zinc chloride catalyst, whereas in case of tertiary, it reacts quite easily. It's just by shaking the alcohol with the concentrated HCl. So this is again because of the reactivity. Tertiary is more reactive than secondary and primary. Due to that, it does not require a catalyst. Next is reaction with HBr, again a concentrated halogen acid. So ROH, that is an alcohol, reacts with HBr, and this is used for the preparation of alkyl halides, and that will be alkyl bromides. Here you have reaction with sodium bromide. So ROH reacts with sodium bromide in the presence of H2SO4 for us to form NaHSO4 and H2O as byproducts, leaving behind the alkyl bromide as the product. Next, reaction with sodium or potassium iodide. So when alcohols react with sodium or potassium iodide in 95% orthophosphoric acid, it forms alkyl iodide. So here it was alkyl chloride, here you had alkyl bromide, and in this case we're preparing alkyl iodide. Next is phosphorus trihalides. Phosphorus trihalides are used for the synthesis of alkyl halides, obviously, but it itself, the phosphorus trihalide is prepared by the reaction between the red phosphorus and bromine and iodine. So you have red phosphorus with bromine and iodine. That's what is written over here. See, red with phosphorus with bromine or iodine, and that gives us the phosphorus bromide or iodide respectively. So here you have ROH, that is the alcohol, reacting with phosphorus trihalide to give us the alkyl halide. The X can be chlorine or bromine. In case of reaction with PCl5, it leads to the formation of the alkyl chloride as the product, as well as POCl3, as well as HCl. And POCl3 is actually phosphoryl chloride, and whereas the last reaction, there is ROH reacting with red phosphorus and X2, that is basically going to be the it can be either bromine or iodine. That's the preparation of the phosphorus trihalide, and that leads to the formation of the alkyl halide. And with that, one more thing, the product which is formed in the first reaction, that is the reaction with PX3, is phosphorus acid. So with that, we're done with the preparation from alcohol. One more thing. I'm so sorry. So alkyl chlorides can also be prepared by two ways. One is either by passing HCl gas through a solution of alcohol, or by heating the mixture of alcohol and the concentrated aqueous halogen acid. And that is what we observed in the above methods. And but the issue with this particular method is the fact that we can't use this for the synthesis of aryl halides. This is because the bond between the carbon atom of the phenol and the oxygen atom are quite stable, and they will not undergo, they will not be replaced. The OH cannot be replaced in the phenol molecule. Next method is the preparation from hydrocarbons. So the first type is from alkanes, and this is by the free radical halogenation. So what happens is, in the presence of UV light, chlorine undergoes forms a free radical, and this free radical leads to the formation of various products. You have learned about this mechanism last year. So this leads to the formation of various products, and they're quite difficult to separate as pure compounds, and that is actually a disadvantage with this method. Next is from alkenes. Now, alkenes react with HX, and this leads to the formation of an alkyl halide. Quite simple, right? But there comes an issue in this case. So if CH and CH2 bond is broken, it can either be broken over here, and the iodine can get attached here or here. So this is basically solved by the Markovnikov's rule, which states that the negative part of the reagent gets attached to the carbon atom having less number of hydrogen atoms. So because of the Markovnikov's rule, you have the iodine getting attached here as the major product, whereas this, in this case, is going to be the minor product. Remember, you would have learned, there's a mechanism also that was involved. Due to the mechanism and the stability of the carbocations formed, the Markovnikov's rule was given, and that states that the negative part, that the iodine will get attached to the carbon atom having less number of hydrogen atoms. Next is by the addition of halogen. So this is also from the hydrocarbons, and this is by addition of from alkenes, it is addition of halogen. So here you have an alkene reacting with bromine and water. So you have direct addition of the halogen atom or halogen molecule, and this leads to the formation of a vicinal dihalide. So vicinal dihalide will have the halogen atom attached to two adjacent carbon atoms, and this reddish, so bromine as such is going to have a very strong reddish color, but when it reacts with the alkene and leads to the formation of vicinal dibromide, the product formed is colorless, and this helps in the detection of the presence of a double bond in a molecule. The last method is by halogen exchange. Here you have two named reactions, Finkelstein and Schwarz. If you notice, till now we did not speak about we didn't speak about fluorine at all in the above reactions. So the reaction which we use is Schwarz for the synthesis of an alkyl fluoride. So what we do is we react an alkyl chloride or bromide. I'm sorry, it is supposed to be bromide. This is supposed to be bromide. It reacts with a metallic fluoride to give us an alkyl fluoride. Okay, I do not know what happened there. So an alkyl fluoride is formed over here, and the metallic fluorides can be AgF, Ag2F2, COF2, SbF3. So these are all metallic fluorides. They will help form the product, which is the alkyl fluoride. Next reaction is the Finkelstein reaction. Here you have an alkyl fluoride or bromide reacting with sodium iodide in triacetone to give us an alkyl iodide with sodium halide. So this reaction, in this case, what happens is the sodium chloride and bromide which is formed will be precipitated out. And because this is getting precipitated in triacetone, the reaction will go in the forward direction. And this is based on the Lee-Chaklias principle. Now, these two reactions are actually halogen exchange reaction, which means one of the halogen has been replaced, one of the halogen atom has been replaced by an other atom. With that, we're done with the preparation of haloalkanes. Let's quickly look over at the preparation of haloarenes. The two methods, one is from hydrocarbons by electrophilic substitution, and the second is from amines by Sandmeyer's reaction. You'll be learning about Sandmeyer's reaction again in amines as a chapter. So first one is from hydrocarbons by electrophilic substitution. So here you have an arene. Arene is reacting with chlorine or bromine, could be either, and this leads to the formation of aryl chloride or bromide. Pretty easy, right? So here we have a catalyst, and that's going to be either iron or iron 3 chloride. So here, if you notice, here you have the toluene, okay, and it's reacting with X2 and leading to the formation of ortho and para products. And these products can actually be separated by because of their difference in melting points. Now, the reason you have ortho and para is because this is an electrophilic substitution, which means An electrophile is going to come attack at this and this position. And because of that, you have the formation of two products. Now, when we're talking about iodine, so in case of iodine, what happens is this reaction can be reversed, which means in the reaction itself, the few of the products which will form will go back to the initial stage. And so to prevent all of that happening, we actually add an oxidizing agent. So what an oxidizing agent does is it reacts with the hydrogen iodide which is formed. And this in turn prevents the reaction from going back to the first step. But in case of, so we talked about fluorine, we talked about chlorine, bromine, but we didn't talk about fluorine. This is because this method cannot be used for the synthesis of fluorine substituted aryl halides because fluorine is highly reactive in nature. Next is from amines by Sandmeyer's reaction. So what happens is when an amine reacts with sodium nitrite, it leads to the formation of something called a benzene diazonium salt. And this, in this case, it's a benzene diazonium halide. This freshly prepared and it reacts with a cuprous chloride or bromide. Okay, that's Cu2X2, and that leads to the formation of an aryl halide. Now, in case of iodide, we're just going to add potassium iodide directly, and the diazonium salt is shook with the potassium iodide. With that, we're done with the preparation of haloarenes. One is from hydrocarbons by electrophilic substitution. In case of chloride and for addition of or for the product to have a chlorine or a bromine atom, we are basically reacting the arene with chlorine or bromine with iron or iron 3 chloride in the dark, and this gives us two products, ortho and para in this case, and these are separated because of their very difference in melting points. Whereas in case of iodine, what we do is we add an oxidizing agent which makes sure the Hi, the hydrogen iodide which is formed, will get oxidized and it will not interfere with the reaction, because in the absence of an oxidizing agent, the reaction is reversible. And fluorine and fluoro compounds are not prepared by this method. Next is from amines. Amines basically they undergo Sandmeyer's reaction, which means this is aniline. It's reacting with sodium nitrite to form benzene diazonium halide. And this benzene diazonium halide is reacting with cuprous chloride or cuprous bromide to give us an aryl halide. But for iodine, it's reacting just with potassium iodide. With that, we're done with the preparation of halogen. Physical properties. Now, physical properties, we'll be covering things like color, smell, melting, boiling points, density, as well as solubility. So let's start with colors. Colorless when it's pure. Bromides and iodides, they actually develop color on exposure to light over time. Smell, they have a very sweet smell, many volatile ones. Melting and boiling point, let's get to that. Oh, wait, this is state. First of all, this is state. Methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes are gases at room temperature, and the higher members are usually liquids or solids. And this is something that we notice even in case of our first alkanes that we studied about ethane, methane, propane, butane. So that's something quite similar. Now, halogen compounds, they are polar. As I told you, the carbon halogen bond is polar in nature, and this is because of the difference in electronegativity of the halogen and the carbon. So halogen pulls the electrons towards itself, and this leads to the polarity of the CX bond. Now, this, along with the higher molecular mass of the compounds, what happens is the intermolecular forces are quite strong in them. And so there are two forces we're talking about in terms of intermolecular, both the dipole-dipole interactions as well as the van der Waals forces are high for halogen atoms. And because of that, it affects the boiling and melting point. Now, as the molecules get bigger, it has more electrons, and so obviously the attraction will get stronger. So the boiling point order becomes highest for Ri compared to RBr, compared to RCl, compared to RS because of the size of the halogen atom. Here we are assuming the R group is the same alkyl group. So in that case, for iodine, for the iodide, it's the highest, and for the fluoride, it's the lowest. This is because as the molecule is getting bigger, the number of electrons are increasing, and it has more number of electrons. So the attraction in the molecule is also going to increase. Now, in case of the in case of the isomeric haloalkanes, the boiling point will obviously increase with increase in branching. And in case of dihalobenzenes, it's also almost the same. So, due to symmetry, actually, para positions have a higher boiling point, higher melting point compared to ortho and beta. Next, density. So density, they are heavier. Bromo, iodo, polychloro, all of them are heavier than water. Now, the density is going to increase with increase in the number of carbon atoms, increase in the number of halogen atoms, and the mass of halogen atoms. Number and mass separated because number could be 10 iodo groups, 10 chloro groups, and mass could be like 5 iodo groups. So because of that, they're mentioned as separate points. So density is heavier than water, or rather density of halogen compounds is heavier than water. The last is solubility. So for a haloalkane, the energy is required for it to be soluble in water. There are two things that have to happen. First of all, as we know, there'll be some amount of interactions between the halogen atoms. Halogen alkyl halides, and there is some amount of interaction between them as we studied above, and this is affecting the boiling and melting point. Now what happens is, for it to get dissolved in water, these interactions have to break. Not only that, they also have to have the hydrogen bonds between the water molecules also have to break, and only if these two happen can the alkyl halides be dissolved in water. But what happens is when it tries to do that, and when it does get dissolved, hypothetically, the amount of energy which is released, or the attraction between the molecule is when and the amount of energy released is actually quite less when the haloalkane and water molecules are going to interact. And because of that, haloalkanes are insoluble in, or rather very slightly soluble in, water. Whereas in case of organic solvents, the new interaction between the haloalkane and the solvent is stronger, and it requires and actually releases some amount of, or rather is stronger than that of the haloalkanes themselves and the original solvent molecule. And because of that, the haloalkanes are quite soluble in organic solvents. With that, we're done with the various physical properties. We started with color, went on to smell, melting and boiling points, density, and solubility. Remember one thing, the basic thing you need to understand is the fact that the CX bond is polar in nature, and that is affecting the various properties that we have observed below. Let's look at the chemical properties of haloalkanes and haloarenes. So first of all, in case of haloalkanes, you have nucleophilic substitution reactions where you have SN1, SN2, and next you have elimination and reaction with metals. In case of haloarenes, you have nucleophilic substitution, electrophilic substitution, as well as reaction with metals. Basically, they're the same. Here you don't have elimination in case of haloarenes. So let's start with the nucleophilic substitution. I will just like to point out that it will be done in detail in the next video. I just wanted to give you a brief idea on this one, and then I'll be doing it in detail again in the next video. So nucleophilic substitution reaction involves the formation of a new bond between the carbon atom and an incoming nucleophile. So nucleophile is nucleus loving, which means it is electron rich in nature. So nucleophile will come attack, and this will lead to the formation of a new bond between the carbon and the nucleophile, and there'll be a breakage of a bond between carbon and the halogen atom. Now, because of the electronegativity difference, you have a partial positive charge on carbon and a partial negative charge on the halogen, and this is why a nucleophile is going to come attack a partially positively charged carbon atom. Now it is initiated by the nucleophile, and so it is called a nucleophilic substitution reaction. So here in your textbook, you actually have the reagent and the nucleophile. So the nucleophile which is going to get attached will decide the kind of product which is formed. For example, an NH3 group, when it's going to come attack the halogen or alkyl halide, it's going to lead to the formation of a primary amine. So based on the kind of nucleophile reacting, you have the kind of products which are formed. In case of cyanides and in case of cyanides, you have CN. So CN can either attack from the carbon or attach themselves from the carbon, or it can attach from the nitrogen. And this leads to the formation of two different compounds, cyanides and isocyanides. So and these are called as ambident nucleophiles because they have two nucleophilic centers. So in case of nitrile also, you have two ways. One is through the oxygen and the other is through the nitrogen. And when it's through the oxygen, it is forming an alkyl nitrile. And when it's through the nitrogen, it's forming a nitroalkane. Now, the mechanism is what is important over here. So you have two mechanisms for nucleophilic substitution. You have SN1 and SN2. So SN1, again, this is going to be very much in brief. I'll be doing it in detail in the next video. So SN1 is going to involve the attack of the OH minus, which is a nucleophile, from behind the carbon Cl bond. So what happens is when this starts to come in and attack, there is a partial formation of this bond between the oxygen and carbon, and there'll be a partial breakage of the carbon chlorine. Basically, this is going to take place simultaneously. When OH is going to come attack the carbon, there's going to be a bond formed, while simultaneously the CCl bond is going to start breaking. Now, all of this will make sure that the CH bonds are pushed away and they're going to be on the plane of paper. And all of this leads to something called as variation, inversion and configuration, which again, I'll be talking about in detail in the next video. So this particular state is called a transition state, which is formed during the course of a nucleophilic substitution SN2 reaction. Now, what we notice from here is the fact that if the if the alkyl halide is quite bulky, it will not undergo nucleophilic substitution in the form of SN2 mechanism very easily. This is because, first of all, let's look at this. Here you have a methyl group, just teeny tiny hydrogen atoms, so the nucleophile can easily attack. But when you have a bulky CH3 groups, which is a tertiary butyl group over here in this case, and you have a halogen, where do you think the nucleophile will have the place to come and attack the carbon atom? Because this involves the attack of the nucleophile on the carbon from the back, we need to make sure that it does not sterically hinder the formation of the product. So when you have this SN2 mechanism, primary halides will undergo an SN2 more than secondary, more than tertiary. And even before primary, we have a methyl group, methyl halide. Next is the SN1 mechanism. So SN1 mechanism, so first of all, SN2, we did not have any intermediate steps. That intermediate which was formed was actually a transition state, and it is quite unstable and very reactive. So the reaction is very fast. Oh, one more, it follows the second order kinetics, which means the rate of the reaction depends upon both this group as well as this one. Whereas in case of our SN1 mechanism, you have the reaction taking place as two steps. So here you have tertiary butyl bromide reacting with OH minus to give us tertiary butyl alcohol. The first step is the cleavage of CBr bond. Now, as we know, the CBr bond is highly polar because of the electronegativity of the bromine atom. Now, what happens is, because of that particular polar nature, the bromine is going to get kicked out, and this leads to the formation of a carbocation. Now, this carbocation is what is going to undergo reaction with the nucleophile, and in this case, if you notice, it can attack either from here or from here. It does not matter, and because of that, you have, the bulky group thing does not affect that much in this case. So the rate of the reaction is dependent on this step because it's the slow step. So this is called the rate determining step. And in this step, you only have the alkyl halide and not the OH, the nucleophile. And because of that, this is called a this is a first order reaction because the rate of the reaction is dependent only on one of the reactants. And order of the reactivity, it's based on the stability of the carbocation. More are the number of alkyl groups. So in this case, 3 alkyl groups, carbocation is obviously going to be more stable because of their electron releasing nature of the alkyl groups. This, however, is not the case. So if it's only 2 CH3 groups, then it will be less stable. And if you just have one, it's going to be all the more less stable. All the less stable. So because of that, the reactivity in case of SN1 is going to be tertiary is more reactive than secondary, which is more reactive than primary. And if a tertiary halide is going to undergo a substitution reaction, it will follow the SN1 mechanism. And if it's a primary halide, it would prefer a secondary sorry, if it would prefer an SN2 mechanism. Now, when we talk about benzylic and allylic, they will be stabilized. The carbocation form is going to be stabilized by resonance, and the reactivity of the halide is iodine. Ri is more than Rbr, more than Rcl, and very high, much more than Rf, and the R is considered as the same alkyl group. Now, with that, we're done with the nucleophilic substitution reaction. This was just to give you an overview. I will be uploading a video in detail about nucleophilic substitution reaction because I found it very difficult when I was in grade 12. So let's start with elimination reactions. So elimination reactions, as their name suggests, basically mean that something is getting kicked out. Okay. So here you have a base coming and attacking the hydrogen, and this bond is breaking, and this leads to the kicking out of the halogen atom as an X minus. Now, this is taking place at the beta carbon. So the alpha carbon is the carbon which is attached to the halogen atom. Beta is going to be the one which is attached to the alpha. Gamma is going to be attached over here, attached to the beta. So that's how it goes. So in this case, you just have like one beta carbon, but there might be cases where you have more than one. And to decide the alkene which is formed is done by something called as the Zaitsev's rule. So Zaitsev's rule was given by this chemist Alexander Zaitsev, and he formulated this rule in the year 1875. Now, what he said was, now, okay, fine, look at this reaction. You have two beta carbon atoms, this one and this one. So it can either attack at this position or this position. So here, when it attacked at this position and double bond was here, this is the product formed. And notice it's only 19%. Whereas when it attacked on the left, it formed a major product of 81%. So there has to be something, right? So what he said was that here, the alkene, which is having a more number of alkyl groups attached to the doubly bonded carbon atoms, is going to be the preferred product. So in this case, this carbon and this carbon, okay, this is attached to one alkyl group and one hydrogen. This is attached to an alkyl and an hydrogen atom. Whereas in this case, this carbon atom is attached to an alkyl and a hydrogen, but this carbon atom is attached to two hydrogen atoms. And because it is following the Zaitsev's rule, it is, I mean, due to that, it is a minor product, whereas this is the major product. I think I learned the reason for the same when I was doing my master's in organic chemistry. So we don't, this is the rule. And remember, more substituted alkene is the major product. So pentoene, so that's what is written over here. So pentoene is the major product. Now, there is a difference between elimination and substitution reaction. So elimination is kicking out and forming an alkene. Substitution is the replacement. So based on the conditions, the decision of following elimination or substitution is decided. First is the nature of alkyl halide. Second is the strength of the base or the nucleophile. In case of elimination, it's going to be a base. In case of substitution, it's going to be a nucleophile. Next is going to be the size of the base or nucleophile as well as the reaction conditions. Now, when you have a bulkier nucleophile, that will act as a base. And if it is going to act as a base, what it's going to do is going to pull the electrons towards, pull the proton towards itself. And this is going to happen instead of it going and attacking the carbon atom, it will go pull out the hydrogen atom. So because it is pulling out the hydrogen atom, it is going to follow the elimination procedure. But if, and this is because of steric reasons, because it can't go in and attack the carbon atom, it prefers just extracting the proton. So primary alkyl halides usually prefer an SN2 mechanism, as I told you, because of the steric factors. Secondary can be SN2 or elimination based on the strength of the base or nucleophile. If it's bulkier, then it will follow the elimination. If it's not bulky, it will follow SN2. Next is tertiary. It can either go for SN1 or elimination is going to be based on the stability or the more substituted alkene. Now, with that, we're done with comparison between elimination and a substitution reaction. Let's look at the reaction with metals. Now, Grignard reagent is one of the most commonly learned reaction preparation, preparatory compound for any functional group. Like if you look at your textbook also, if you'll have a Grignard reagent being used for the synthesis of an alcohol, it will be used because of its versatility. So organic chlorides, bromides, iodides, they generally react with a metal. Okay, and this leads to the formation of a carbon with a metal bond formation. Okay, so there's going to be a bond formation between a carbon atom and a metal. And these compounds, where there is a C and a metal bond, that they are called as an organometallic compound. And Grignard reagent is one of the most commonly known, one of the lot. So our MgX is Grignard's reagent. So haloalkane is reacting with magnesium metal, and in the presence of dry ether for us to get Grignard reagent. Now, this bond between the carbon and the magnesium atom is going to be covalent, but it's going to be very polar because carbon is actually more electronegative than magnesium. And whereas in case of magnesium and the halogen atom is going to be an ionic bond. For example, NaCl. NaCl is an ionic compound, right? So similarly here also MgX is going to be an ionic bond. The activity of Grignard's reagent is highly reactive in nature. That is why you have dry ether. Dry ether means even one single water molecule is also not present. So dry ether is used to make sure that this reaction does not get affected and you get the proper product. So it is highly reactive, and on reaction with metal, we get the alkane and the MgOH. This actually can be used for the synthesis of a hydrocarbon from the alkyl halide. Now, this reacts with any source of proton like water, alcohol, amines. They are all quite acidic for the conversion of the Grignard reagent to the hydrocarbon. Now, that's why we are saying that there can be no traces of water. The last one is Wurtz reaction. Now, Wurtz reaction is also carried out in the presence of dry ether, which means in the complete absence of water. And this is not because of the reactivity of in this case, it was reactivity of the RMGX. And I think in this case, it's because of the reactivity of sodium. Sodium in the presence of water, it leads to an explosive reaction. That's something we don't want, right? So what happens is the hydrocarbon which is formed, here you have Rx. So Rx plus XR, you have the formation of an RR bond plus NaX. So this is done in the presence of dry ether. With that, we're done with the reactions of haloalkanes. We started with the nucleophilic substitution reactions, SN1, SN2. In brief, I didn't touch about the stereochemical aspects, which I will be doing in the next video. Then you have the elimination reactions and the reaction with metals. Let's quickly look over the reaction of haloarenes. Now, reactions of haloarenes, first of all, we start with the nucleophilic substitution reaction. Now, these compared to alkyl halides, the aryl halides are less reactive towards nucleophilic substitution reaction. This is because for nucleophilic substitution reaction take place, the Cl group has to get kicked out. But because of resonance, they don't want to let that go. So here you have a partial double bond character coming in, and due to the conjugation of pi electrons across benzene ring, this leads to the unreactivity of a haloarene towards the nucleophilic substitution reaction. Next reason is the difference in hybridization of carbon atom in the CX bond. So here you have an haloalkane and a haloarene. Here the carbon atom of a haloalkane is sp3 hybridized, whereas for an haloarene it's sp2 hybridized. So S character in this case is going to be lesser than this one. So what happens is because of the less S character, the carbon atom is more electronegative, and it has the capability of pulling the electrons towards itself. But because in this case, it's actually less, and it's going to be less electronegative, and it does not pull the the electrons towards itself compared to that of a haloarene. Because of that, the bond length of a CX bond is actually higher than a CX of the haloarene. And obviously, it's difficult to break a shorter bond than a longer one. And because of that, haloarenes are actually more or less reactive towards nucleophilic substitution compared to haloalkanes. Now, there is also another reason, instability of the cation C6H5 plus. So C6H5 plus basically means that chlorine has been kicked out and you have a positive charge on the on the benzene ring. So here, instead of chlorine, you'll have a positive charge. And this is not very stable. And this is because what happens is when the Cl minus Cl got kicked out, there you have a positive charge, right? Now, this cannot undergo resonance with the rest of the electrons. And because of that, the structure which is formed is quite unstable. And because of this, the carbocation formation, that is the SN1 mechanism, is not possible for an haloarene. Next, repulsion. Now, nucleophilic. So the reason you have so many electrophilic reactions, electrophilic substitution reactions, is because of the fact that our benzene ring is highly, it has a high number of electrons. So it's electron dense or electron rich. Nucleophile is in itself electron rich, and so it cannot easily attack an arene because of the repulsive interactions. However, in extreme conditions, as always, we will force the compounds to undergo reaction. And so here you have various reactions. So here you have NaOH, so you have chlorobenzene, and it reacts with sodium hydroxide at 623 Kelvin and a pressure of 300 atmosphere. We are getting phenol. Now, if we have electron withdrawing groups at ortho and para positions, the reactivity actually increases. Now, the reason this is the case, and this is not the case for meta, we don't even talk about meta over here. We only talk about ortho and para. Now, notice the difference in reaction conditions. You just have it at para, you have 443 Kelvin, but you have it the nitro group, which is electron withdrawing at ortho and para, it is the temperature is decreasing to 368. And if it's just warmed up, you get in case of this case, here the NO2 groups, the electron withdrawing in nature, there are 3 of them. They're at ortho and para positions. The solution just has to be warm, and we're doing it in the presence of water. We're not even using a very strong acid. Now, the same is not noticed for meta. Now, let's look at the structures which are involved. So when the OH comes and attacks the carbon bound to Cl, this bond is going to shift to the adjacent carbon atom. Okay, and this will lead to a formation of a negative charge. Okay, as I told you, we'll not be following the phenyl carbocation because of instability. So it's not stable, so that's ruled out completely. Here, however, you have a negative charge that's going to get delocalized overall, right? So when you have an electron withdrawing group at the ortho and the para position, they will make sure these structures which are formed in the intermediate are stable. So here you have a negative charge, and then it will shift to this para position, and then it's going to go back to the ortho, and then this coming here, and the chlorine is going to get removed for us to get an OH alone. So when you have an NO2 group at the ortho and the para position, what is happening is the negative charge is going to get pulled by the NO2, and this will in turn stabilize our intermediary which is formed. So the first step is going to be a slow step, but the removal of Cl is going to be a fast step. So again, over here, you don't see it. So in case of this case, here you have a meta isomer which is being considered. Because here it's ortho and ortho para, you have negative charge at those 2 positions, and so it's helping out. But in case of meta, if you notice, you don't have a negative charge at this carbon atom. So it does not really help for the NO2 to pull electrons, because that does not have a lot of effect. So because of that, we only consider the ortho and the meta isomers. So with that, we're done with the nucleophilic substitution reaction. There are 4 reasons why it is less reactive towards nucleophilic substitution. First is the resonance effect. Resonance effect makes sure there's a double bond character between chlorine and the carbon atom of the benzene ring. Next is the fact that the hybridization of the carbon atom is different in both cases. In case of haloarenes, due to the electronegativity of the carbon atom because of the less S character, what is happening is it itself capable of pulling the electrons towards itself, and this in turn shortens the bond between carbon and the halogen. And this shorter bond implies that it's less reactive towards the haloarene, incoming nucleophile. Next is the stability of the phenyl cation. Phenyl cation will be formed when the chlorine is going to get kicked out, the halogen is going to get kicked out. And the moment that happens, you have a phenyl ion which is highly unstable, and that is why the SN1 mechanism is not being considered. Next, the arene is in itself an electron-rich group. A nucleophile is also going to be electron-rich, so there will be repulsion, making it very difficult for the nucleophile to come and attack the arene. So what we do is we try and react it anyways. So here you have variation. So first of all, we're replacing the chlorine group with the hydroxyl group, leading to the formation of phenol. Notice there is a difference in terms of the reaction conditions. In the absence of any electron withdrawing groups, it was done at 623 Kelvin at 300 atmosphere pressure. But when there was a para substitute electron withdrawing group, then the temperatures decreased to 443, and when it was at ortho and para, it decreased to 368. And even when you had like three groups at ortho and para position, it was just warmed. And this is because of the stability of the structures. So the presence of electron withdrawing groups at the ortho and para positions is making sure that the negative charge is getting delocalized, is pulled by those, and that in turn stabilizes the intermediates which are formed, or resonance structures rather, which are formed. Next is the electrophilic substitution reaction. Now, halogens are very unique. Generally, we learn, okay, this is an electron releasing group, this is an electron withdrawing group. Okay, if it's an electron releasing, the ortho and para position are going to be electron rich. If it's electron withdrawing, the meta position is going to have an electron rich, or that's because of the positive charge. Anyway, that's what you learned last year. One thing you don't touch into, like you don't study about deeply, is the fact that halogen atoms are slightly deactivating as well. So halogen atoms can act, due to the lone pair of electrons, they can act as ortho para directing in nature. Okay, and this in turn increases the density at the ortho and para positions. But halogens themselves are actually highly electronegative. So they are minus I groups. So they are ring deactivating compared to that of a benzene ring. So that's one thing you need to remember. So halogen atoms are slightly deactivating due to the minus I effect of the halogen because of the electronegativity. So electrophilic substitutions in haloarenes are also going to require extreme conditions. First is halogenation. Halogenation is basically haloarene reacts with chlorine, and in the presence of anhydrous FeCl3 as the catalyst, is leading to the formation of two products, 1,4-dichlorobenzene and 1,2-dichlorobenzene. So 1,4 is going to be major, 1,2 is going to be minor. Now, I would like to give you some time to contemplate as to why the 1,4 is major and 1,2 is minor. By the end of the electrophilic, we will discuss the same. So in case of nitration, it's going to react with concentrated HNO3 and concentrated H2SO4, leading to the formation of a nitro compound. And the nitro group is going to get substituted at the ortho and the para positions respectively. Next is sulfonation reaction. Sulfonation reaction, you have the reaction with concentrated H2SO4 leading to the formation of benzene sulfonic acid. And again, you have two products, para and ortho. Friedel-Crafts reaction is so Friedel-Crafts reaction are named reactions. Basically, what happens is haloarenes are reacting with acyl or alkyl chlorides, and this is leading to the formation of two products. When it reacts with an alkyl chloride, it leads to the substitution of the alkyl group. When it's with the acyl chloride, it is leading to the formation of a COCH3 group. So you have a phenone form, acetophenone. Acetophenone group, or I'm so sorry. An acetyl group is getting getting substituted at the ortho and the para position. Now, if you notice, all of these cases, our ortho position product is the minor one, the para is the major one. The reason this is the case is because in case of our ortho product, you have the steric hindrances taking place. So there are going to be repulsions between this big chlorine and this group NO2. And due to these repulsions, the ortho products in all of these cases are the minor product. Even in alcohols, phenols, ethers, you learned that the ortho products are minor, whereas the para products are major because of no steric hindrance at the para positions. The last reaction, our reaction with metals. Woods reaction, again, we learned Woods in the previous for haloalkanes as well. So alkyl halide is reacting with sodium as well as aryl halide in the presence of dry ether, because sodium is highly explosive, to lead to the formation of an alkyl arene. So benzene with an R group. Again, this has to be taken place in the presence of dry ether, no amount of water whatsoever. Next is phytic reaction. So aryl halide is reacting with sodium in the presence of dry ether. It's similar to the Woods reaction for haloalkanes. So that the two benzyl groups are going to be bound to give us a diphenyl group. With that, we're done with reactions, chemical reactions of haloalkanes and haloarenes. Notice both of them have the same set of reactions. You have nucleophilic substitution, elimination, and reaction with metals. But in this case, instead of elimination, you have electrophilic substitution reactions as well. So, and you don't have elimination because the Cl bond is actually quite strong. So with that, we're done with the chapter Haloalkanes and Haloarenes. In the next video, I will be uploading a detailed explanation of the SN1, SN2. For some reason, I've always found it very difficult. So I will make sure it's easier for you guys. And do check out the other videos for the other chapters that have already been uploaded in this playlist. With that, we're done.